One of the most desirable properties of a mathematical proof is elegance, the indescribable property of proof that makes it beautiful. But why do we care about beauty in math? Math is not art. This should not matter. Yet we still strive for elegance, and in this video I will show an example that explains part of the reason why. I will try to illustrate that elegance leads to insight, which eases generalization. Okay, so here's the problem. If we have n random lines, how many regions do they divide the plane into? Random, meaning that the lines aren't special. There is no point where 3 lines intersect, and no 2 lines are parallel. It may seem like there are multiple answers. Doesn't the arrangement matter? But it turns out that as long as the lines aren't parallel, and there are no triple concurrences, there is exactly one answer. For example, if there is 1 line, then the plane will be cut into 2 regions. 2 lines gives 4 regions, and 3 lines gives 7 regions, no matter how we move them around. One way to solve this problem would be to employ Euler's formula, v minus e plus f equals 1. While it might be the first idea that comes to mind, it is not particularly elegant. Using this to calculate the number of faces is a fun combinatorial problem if you want to try it. But it is nothing more than a counting problem and gives no insight as to why. Moreover, it is hard to generalize this, for example, to planes in 3D space. Instead of taking the easy route, I will show you a longer and more beautiful route that starts with simplification. How many regions do endpoints cut a line into? N plus 1 obviously, but how does this help? Well, the easiest way to see this is that you start at the region at the end of the line, and every time you encounter a new point, you encounter a new region. Along the way, you encounter n points, so that's n new regions plus the original one, giving the answer n plus 1. Okay, but how does this generalize? If we start as the point at infinity and move in a path, we will probably not encounter all the points, let alone all the regions, so this does not seem promising. But we are missing something. Before, we were breaking up one-dimensional space with zero-dimensional objects, and we moved a zero-dimensional object through the space to count. Now, we are breaking up a two-dimensional space with one-dimensional objects. By analogy, we should move a one-dimensional object through the space to count. Let's try again with this in mind. So we start with a line at infinity. Each of the original lines will intersect with this line once, so it will be broken into n plus 1 regions by those intersections. So we see those n plus 1 regions to start. Great. Next, let's consider moving the line up. By analogy, whenever we encounter a line, we should see a new region? That can't be right. We already intersect with all the lines, and we never encounter a new one. But let's still try and see what happens. Okay, so whenever we encounter a point where 2 lines intersect, we encounter a new region. We already saw the left and right regions, but the top region is new, and we stop seeing the bottom one. Our line still intersects with n plus 1 regions, it's just that the top region has replaced the bottom one. As n lines intersect at n choose 2 points, and the line originally intersects with n plus 1 regions, the total number of regions we see is 1 plus n choose 2. That's a neat proof, right? Certainly more elegant than the combinatorial argument we could have used in conjunction with the overpowered Euler's formula. But this elegance also allows us to generalize. 1 plus n choose 2 looks awfully like n choose 0 plus n choose 1 plus n choose 2. If we extend to 3 dimensions, do n planes generally divide space into n choose 0 plus n choose 1 plus n choose 2 plus n choose 3 regions? Yes! If we look at a plane at infinity, the original n planes divided up into n choose 0 plus n choose 1 plus n choose 2 region, because the intersection of each of them with the plane is a line, and we know how many regions n lines divide the plane into. Then, as we move the plane up, we will encounter n choose 3 intersections of 3 planes, or points, each of which leads us to encountering a new region. Therefore, once we have moved past all the interesting points, we will have seen n choose 0 plus n choose 1 plus n choose 2 plus n choose 3 regions, and in k-dimensional space, we will see n choose 0 plus n choose 1 plus, and so on all the way up to n choose k regions in total. By taking a step back in order to think and see a more elementary but winding path, not only were we rewarded with the sight of a more elegant proof, but of a more generalizable one. While one could generalize the use of Euler's formula and count all the various intersections of various dimensions, doing so would be an algebraic mess to slog through, and even then, one would have to be inspired by something to come up with a formula as memorable as n choose 0 plus n choose 1, and so on, all the way up to n choose k. It is probably the simplicity of this argument that makes it feel mathematically beautiful. And unlike painting a picture or writing music, this beauty is not only aesthetically valuable, but it gives us further insight into the world that the filth of more utilitarian methods obscures.